Okay, let's get slightly more complicated with the oriented bounding box. The oriented bounding box, or OBB for short, is still a box. It's any kind of rectangular shape, but now it can be rotated to an arbitrary angle. Whereas with the AABB, we knew that the separating axis had to be either the x-axis or the y-axis because the bounding box was aligned with those axes. Now we have boxes that don't have to be aligned to the x-axis or the y-axis, and they don't have to be aligned to each other either. As you can see in this example, the green box and the purple box, they don't intersect. You can clearly see that they don't. But the y-axis here shows an overlap between those shapes. And the x-axis also shows an overlap between those shapes. So we're going to need something else. What we do with an OBB is we create new axes. We create 4 of them, one for the length of each OBB and one for the width of each OBB. And by the way, I'm talking about two-dimensional here. So in this case, I've gone ahead and selected the one that you can tell kind of by the eyeball method is going to be the right one. In general, you'd have to try all 4 of the axes. But let's just jump to the one that we think is going to be right. So I'm going to take this axis here, this direction, to be the axis, and we'll project both shapes onto that axis. And you can see I've already sort of pre-projected the green shape onto the axis and the purple shape onto the axis. I ran out of space here. The purple shape should go a little further down, but I ran out of space. Okay, how do we do that? Let's do some calculations. First of all, let's calculate what that axis is. The axis that we're talking about is the side of the green shape that connects, and I can either use this edge or this edge, but it's got to use one of those edges. So I'm going to use the front edge here, the one I've indicated with the dotted line. To calculate that, all I do is subtract those 2 points. I've taken the 0, 3 and subtract the 1, 1 to create a vector pointing that direction. Now, that is not a unit vector. I have a direction vector here, but it is not a unit vector. I don't care. All we're looking for is that the shapes do or do not overlap on this axis. We don't care what the scale is, and so we're going to leave that as not a unit vector. So here we have the axis is -1, 2. What we do next is we project both shapes onto that axis and find what is their minimum on that axis and what is the maximum on that axis. How do you project a shape onto an axis? Well, you can project a point onto an axis with a dot product. That's right, it's always a dot product. So let's take this point here, this point of our green shape, and project it onto that axis. That is this, 1, 1 dot with the axis, which is -1, 2, equals 1. Okay, we found 1. And we would also project, this point on there, and we would get something greater than 1. So we find that, the minimum here is 1, and then we'll have a maximum up here, whatever that is. The next interesting point here is we'll project the purple shape onto this axis as well. Now, the 2.5, 1.5, I'll project that one onto the axis with the dot product, and I get 0.5. So what do I see here? I would, presumably I would do all 4 points of the purple shape. I would find the minimum, and I would find the maximum. I should find that the maximum is this 0.5 we just calculated. And I would do the same thing for the green shape, and I would find the minimum and the maximum on the green shape, and I would compare, and I would say that the minimum of the green shape was 1, and the maximum of the purple shape was 0.5. Therefore, we have a separating axis here, and the 2 shapes do not overlap. Okay. Now that was for a 2-dimensional case of just, rectangle versus rectangle. When we go to 3D, naturally we're going to need to extend to more axes. 2-dimensional shapes need 4 axes, 2 for the one box and 2 for the other box. Now, for a three-dimensional shape, you can imagine, of course, each shape has 3 axes as opposed to 2. And then, so that's 3 axes for shape 1 and 3 axes for shape 2. You might guess we need 6 axes here. But actually, you're wrong. We need more than that. I'll try and do an example of this in class to show you better, but here's a diagram trying to show you. What I've got is 2 three-dimensional boxes, and they're aligned edge to edge. And if you align them edge to edge, you can clearly fit your credit card. This is my credit card. I've slid it through. No problem. But which axis is the separating? Is it this axis? No, because that cuts right through the credit card. Is it this axis? No, that's not it. Is it this axis? No. This axis? No. It's none of the faces of the cube, of either cube. None of the faces of either cube is that green plane. The green plane is made up by combining the edges of opposite cubes, right? That is, this green plane is made by taking this little edge that's sort of, going like maybe into the screen here from that cube, and the top edge of this other cube. And together, those create a plane. And that is the plane of the green. So that is the 9. It turns out there's 9 combinations you have to make. And you get them by, taking the cross product, as you would for any plane. You say, oh, it's the normal of this plane is perpendicular to these 2 edges. So you do cross product. You probably remember that one. Okay. Now, for this class, I am not going to make you memorize this. You don't have to memorize the number 15. You don't even have to remember how to get these axes at all. I will expect you to remember that it's more than the 6 that you can think of, right? This is a legit question. You might see this in a job interview somewhere. It's pretty esoteric, but you might see this, and that's why I want you to know it. How would I approach a question like that? I would say, oh yeah, for OBBs in 3 dimensions, I remember that it's more than just checking the axes of the boxes. There were a few more axes you also had to check, but I don't remember where you got them from. I'm going to have to look that up. And that would be a perfectly good explanation.